Hi, my name is Michael Yosley, and this is part 2 of the final project for design of Aerospace Experiments. We're going to be doing a 2D simulation of fluid flow over a flat plate. As you can see, I have the ANSYS Workbench pulled up. So we are going to drag the fluid flow Fluent into our workspace. First, we will left click on this. We're only doing a 2D analysis. And then we will right click on this. I prefer to use the design modeler. You can also import your geometry from SolidWorks or use the space claim. I just prefer the design modeler. Alright, we have design modeler pulled up. And this is going to be a very simple structure. Our flat plate. First, we need to change the units. We got our measurements for this one in inches. And our flat plate is going to be 6 inches by 0.1 inch thick. So we're going to go 3 inches forward, 3 inches backwards, 0.1 inch down. That is our flat plate. We want to zoom out. And I used 8 inches forward, 10 inches up to make a 16 by 20 fluid area last time. That seemed to work well. Well beyond what we need to make sure our blockage ratio is good. Sketch 1. Concept surfaces from sketches. Sketch 1. Apply. Generate. Now we're going to go in here, surface body. Make sure we change this from solid to fluid. Generate one last time. Go back to our workbench. I had some issues last time. I'm not 100% sure what was causing them, so we're going to click update just to make sure. Then we'll double click on mesh. Okay, now that our geometry is populated into our meshing, click on mesh. The only thing we're going to change here is turning on adaptive sizing. And because it's the default mesh settings, it should generate pretty quickly. There we go, and now we're going to go through and create our name sections. So left click to select, right click to pull up the naming. We're going to name all 4 sides of our flat plate so that we can select them later on when we're doing our coefficient of drag. It'll also help us with the inflation portion that we're going to do next. Name selection here. Now this is our inlet. Our outlet. Go over here, all of those are created. We're going to right click on mesh and insert inflation. Geometry. This is the main surface structure. Boundary method, we're going to select all 4 of these sides. Make sure it says 4 edges. And I used these settings last time. We're trying to get a look at what's going on in that boundary layer. So we're going to set those up like that. This mesh will take a little bit longer to generate. If you have a faster computer, you can go to mesh, set the sizing a little tighter, increase these layers, but this should give us a pretty good view of what's going on in that boundary layer. Got that. We'll zoom in so you can see how it's a little tighter around the actual flat plate. That should give us pretty good analysis of the boundary layer. We'll update this. We'll double click on setup. Alright, we have to close this setup first. Okay, now we've got our setup pulled up. Make sure we have the energy equation off. We're going to change this. We know that our flow is going to be laminar because we're only going 10 meters per second. Materials. You can double check these, but the default is air. Our boundary conditions. It's our velocity inlet, so we'll set this to 10 meters per second. Okay, next we'll go to reference values. Compute from inlet. Make sure all that's good. Double click methods, coupled. We do not want to select a pseudo time method. Okay, our report definitions. Now this time it's a flat plate, so what we're looking for is just the drag coefficient. Because it's symmetric, lift coefficient should be 0. Now this is why we created all these name sections, so we can pick all of those. You can do per zone just to look at what the difference is. Set that at 10. Put print to console, select OK. Close. Our monitors. We're just going to add a couple zeros in these. A little more precise. Okay. Initialization. Standard. Compute from inlet, our 10 meters per second. Initialize. A run calculation. We're going to do 600 iterations. That'll be enough to get us pretty good results without bogging down the computer too much. Alright, that took a couple minutes. We'll see what we got. First, let's take a look at our drag coefficient. Compute that. 0.00186. And see, this is what happens when you have it break down by parts. See the top and bottom from the skin friction. Alright, then the next thing we're going to want is our velocity contours. We'll name this velocity. Easy enough. Velocity. We don't need to select anything. Save and display. And we're actually leave that like that. It's our velocity contour. Zoom to area. You can see what's going on right around the flat plate. You see we have our no slip condition, so velocity 0. There's our boundary layer. Now we're going to do this to look at the velocity profile. That's magnitude. We're going to put that at 10 because we don't want to bog it down too much. We can add more. Let's try 0.5. Velocity, magnitude. Filled arrow. That's what we want to do. Okay, so we've got 0.5 and we've got 2. Now let's zoom in and see if this is giving us the kind of graphics that we want. Okay, let's zoom back out. Okay, so I've made some adjustments to make this a little easier. We want 0.1 for our scale. We want to go in here, draw our mesh, select the wall surface body, top, rear, front, and bottom. Velocity 0.1, skip every one. Save and display, close. Now we can zoom in. And you can see the velocity profile right here. 0 at the surface, increasing until it's the free stream velocity. And you see as we go closer to the front of the plate, it gets to the free stream velocity speed a lot faster. So we go back towards the rear, get to the closer to the fully developed flow. Okay, the next thing we're going to look at is the skin friction on the surface of this plate. Go to XY plot. Wall fluxes. Skin friction coefficient. And we're going to want to look at this on the top surface of our plate. Go in here. Do the center line one. First we'll save and plot. So that's what our skin friction coefficient looks like. You can also change this so that it's the curve length. Should give us a little better graph. That way we're just going from the front to the end of our flat plate. And then you can write to file. That'll give you a text document that you can pull up, drag into Excel, and do any type of further analysis that you need to do on it. We're going to do that for our next one, which is looking at the boundary layer velocity profile. Now we already saw with the vectors, but in order to do this, we're going to do it at the midway point of our flat plate. And to make these surfaces easier, we're going to put x equals 0 because we centered our flat plate. And y equals, we're going to go 0.006. And that's because I've calculated the boundary layer. And I've done this simulation before, and 0.006, even though it's much farther out than the boundary layer that you would calculate, it seems to be about where the velocity equals the free stream velocity. So this is just creating that line. And so while we're in here, we're also going to create the line for the end, which will be at x equals 0.0762, because this calculation is in meters and our flat plate was in inches. So now you have to make sure to change both of these, 0.0762, 0.0762. And this will be a line going vertical at the end of our flat plate. Create, close. Now, we'll change this to velocity. Velocity magnitude, that'll work. We'll change this to curve length. And we'll start off with velocity profile at the middle. Save and plot, that's a pretty good looking graph. And let's see what we got at the end of the flat plate. As you can see, it curves out a little bit more there. So then you'll want to write to file, write that, and it will give you something that looks like this. And then you will copy all of these, copy all those, and you'll drag them into your Excel. So what I've done here is calculated, this is the velocity that they've given me from Fluent. This is the velocity that I've calculated using this equation right here. This is our y. And you can see our theoretical seems to increase in speed a little quicker and reach that free stream velocity, which is what we predicted with our boundary layer being lower than it shows in those graphics. So that's pretty much all we're going to do for today. You can go back through, use these plots to write your files, manipulate those numbers in Excel, get some good looking graphs to represent your data. Alright, thank you for joining me. And that concludes our final project, part 2, analysis of a flat plate in Fluent.